Det var fortfarande samma.
What? Yeah, it looks like fine.
The question is why why it's such a countdown, but
Okay.
doesn't really matter.
Jo, men det kommer det. Jag håller på med en sökgrej.
Det kommer.
Det är på andra.
Ja, det är alltså andra sätt och en felmeddelande som inte vet vad det är.
Nice. Yeah, now it's working. Okay, I think it's time to begin with today's lecture. And as I mentioned last time, in this lecture we will be talking more about algorithms, what an algorithm is, and why, what is the importance of an algorithm, and we will also look at few important algorithms for searching and sorting the data, like selection sort and merge sort and the binary search. And another important part will be about time complexity. So how, if you have, for example, as we said, see that we have like we can have a number of different data structures. So if you have a problem, and the problem obviously involves some kind of a data, and to process that data you have a number of different data structures that you can use, such as stack, queue, and hash set, hash maps, tables. And we saw in previous lecture that each of those different data structures, they have their own kind of characteristics. So for example, some allows data to be stored in kind of some order, and some allows maybe duplicates, and then based on these different characteristics, their efficiency or the performance for the different operations varies. So similarly, we have different algorithms. So an algorithm simply is like a step-by-step kind of instructions to solve a problem. So we have, I mean, if you have a problem, so that problem can be solved in a number of different ways. So depending on your own creativity and the way you design and the whole. So for example, if somebody asks you to organize the chairs in this room, so you can organize it in a number of different ways. So some people can start maybe from the bottom, from the back end. Some can start from the left side, from the front, doing it one chair at a time, doing it maybe two or more chairs at a time. So there can be a number of different ways. So similarly, we can have for one problem you can have a number of different algorithms. So for example, in order to sort the data, maybe you can do it in a different ways, starting it from a smaller number, maybe starting out from a larger value, or maybe from the middle. So there could be a number of different ways. And based on the way you solve a problem, maybe some guy, the working approach for one guy could be very time consuming. I mean, of course he solves the problem, but maybe he takes more time. But then maybe another guy could come up with some smarter solution that can solve the problem in just a matter of few seconds. And also it could be other than the time, an algorithm or the way that you choose to solve a problem could also vary in terms of how much resources you require. So for example, one guy can solve a problem just by own, and maybe another guy needs two other guys to support him. And similarly, when you are writing a program, of course your program requires some computational resources. So it requires some memory, some processing time, CPU time, and it could also be like consuming some power. So because nowadays the computing or the software system, they are becoming more and more variable. The computer is coming closer to our body, so we can use it in a smaller devices like smartphones. And power is one of the critical problems for the software system. So if you have smaller devices with a limited power bank, and then maybe you also need to think about your computation in terms of how much power it consumes. So we have a number of different parameters, and based on that parameter you can choose about different algorithms. And we will talking about time complexity. So how much time an algorithm takes to solve a problem. So if, for example, if you have written a program to solve, let's say, some task in your assignment, and if you want to estimate that on average how much time that algorithm takes to solve the problem. So we'll see, I mean, what are the factors that you should consider while making a time complexity estimate. So starting from some general introduction. So an algorithm is simply an unambiguous description to solve a problem. So why unambiguous is important over here? Because I mean, if there is an ambiguity in your algorithm, so then maybe it's not a useful. So maybe you can use it and understand it, but you cannot give it to somebody else to solve that problem. So it's very important that it's like a recipe, so or maybe a user manual. So for example, if you want to bake a cake and you get a recipe, and in the recipe you get some instructions like how much milk you need, how much eggs, or maybe the baking powder you need, and then you have to put them in the right quantity. And if the recipe is not very clear, if it just says like add some milk, some could be like for me some could be just maybe 2 tablespoons, or maybe for somebody else it could be like 2 deciliters, another guy maybe 1 glass. So it must be like very precise and clearly specified. So otherwise, I mean, it could lead to some not correct results or erroneous results. So maybe it solves the problem, but doesn't solve in the right way. And the history for the algorithm, it dates quite back. Like one of the first well-known algorithm is from mathematics, the Euclidean algorithm to find greatest common divisors. So if, for example, if you have studied mathematics, so I hope you will be aware by this greatest common divisor thing, to find the largest element or factor that divides 2 numbers equally. And this algorithm was presented by a Greek mathematician with the name Euclid. And the name algorithm, it came from a Persian guy, Al-Khwarizmi, and he gave us the algorithm for addition and subtraction. He was also a mathematician. And from his name, algorithmus, we got this word algorithm. So that's just some historical background. So it's not really quite important from computer science point of view, but just as a kind of a background. And then, as I said, that algorithm is simply a set of instructions, okay, to solve a problem. So, and if somebody asks you like, and of course, I mean, when there is an algorithm, there must be some problem on the back end. So let's say we have a simple problem to wash the hair. So can somebody tell me the steps how a lazy guy like me will go to wash his hair or her hair? What are the common steps when we go to wash the hair?
Go to the shower.
Go to the shower. Is it clear? Is it ambiguous or not? Yeah, maybe just go to the shower with your shirts on, or should you take your shirts off? Okay, so yeah, I mean, this is like a simple description to solve how should you. I mean, one of the very first step, as you said, that go to the shower. So you need to wet your hair, and then you need to apply some soap or shampoo, and then you have to rinse it, and maybe you have to do it once or twice, depending on how messy your hair are. Okay, so and the end result is like you should have. Why you need to wash your hair? Because you want your hair to be clean. Maybe after some sports or gym, you get some sweat, and you want to be clean. Okay. And in a similar way, I mean, if, for example, for a mathematical problem, if you want to find a prime number, if you have given a number and you want to find whether the number is a prime number or not, So for that, I mean, we know that the prime number is one that is divisible by only itself. So it should be a number larger than 2 or larger than 2, and then it is not divisible by any other number, by other than itself. Okay. So we need that. How can we find out? So starting from the number 2, and then we keep on dividing it and finding the modulus. So if you find out if that the number, for example, here. So we have steps 1, 2, 3. We take a variable with the name of test, and then we check whether the number n, and if you divide it by 2, does it returns a 0 or not, and then you increment the n by 1. Okay, and in the end, this loop will continue until the remainder is not equal to 0. And if the remainder is equal to 0, then you get out of the loop and test. Okay, if n is exactly equal to the test, and means like the same number, then it means it's the number is a prime. Otherwise, it's not a prime. Okay, so basically, this is not like I mean, when we talk about the algorithm, of course you can write algorithm in a natural language, for example, in your own mother language, Swedish, English, or whatever language you speak, and you can write it in a programming language, or maybe you can write it in some mathematical, using some mathematical notation. We will see about that. Again, what is important for an algorithm is that it should be unambiguous, and it should provide you with the correct results every time. It could not be like once you call or implement, if one guy implements that algorithm, he gets a different answer, and another guy implements that that algorithm, he gets a different answer. So 2 plus 2 should always be 4. It cannot be like sometimes you call the program and it returns you value 4, but next time when you call it, it maybe returns you value 0 or 10 or something else. So it's very important. And then it's also important that the number of steps in your algorithm must be finite. Okay, if it's like an infinite, then it's a never coming to an end story. So for example, in case of a pi, so if you have to compute, if you want to compute the value of pi, so we have a formula over here, and it's an infinite sequence. So it's important that when you define an algorithm, there must be a finite number of steps. But then the question comes, why we need algorithms? So can you suggest me why we need this kind of like recipes or user manuals or steps to solve a problem? Why I mean, any idea? Yeah. Yeah, share. Yes, to communicate. So if we imagine that, so nowadays, I mean, the most of the problem that we know, they are already solved. So for example, most of the algorithms, they have been already defined by somebody, like Euclidean algorithm, or maybe the selection sort, or the different algorithms for the searching. But let's say if we have a problem at hand, how to make the world more peaceful, or maybe, and you want to define an algorithm, okay? So one of the common reason is that why the algorithm is important is, or why we need an algorithm is, of course, if you have, let's say that we go back like 600-700 years back in the history, and there is no algorithm to find, let's say, the greatest number in a list, okay? And you walk down out and you find out the solution for that. Now, you know that there are other peoples. This problem is common for the other peoples, and you want to share with them. So it's very important that you need to document the algorithm. And if you can document the algorithm, so for example, then you can distribute it, then you can communicate it, publish it, and you can help your other fellows or the mankind, okay? So for the communication, yes, and then also there might be different algorithms for the same problem. So one algorithm defined by you, maybe another algorithm defined by a guy in Germany, or maybe in another department or in another university, and you want to compare them, which one is the best algorithm, okay? So if you don't document it, of course, I mean, it's harder to make a comparison. And also, I mean, as a programmer, it's also very nice that before writing a program, of course, I mean, you can start writing a program without an algorithm. Okay, you get a rough, sketchy idea in your mind, and you start implementation it. But maybe if you don't work on the steps, you might in the middle you find out that you got a bad start. Okay, so you forget some of the important things. But it's always recommended that before writing a program, you just first take a paper and try to identify some design for your program, or maybe some steps for your program. So what kind of variables you need, and what kind of operations you need, and so what kind of statements or data structure you need. Okay, so that will help you to maybe solve the problem in a better way. So let's say we have another problem, again, like a common trivial problem that if you have a deck of cards that we use to play different games, and if you want to sort it, so how can you sort? Okay, so here we have an algorithm. One approach is that, we know that in a deck of cards you have like 4 different suites, or the piles, like the clubs, diamonds, spades, and one way is that you separate them in each category, and then you order them according to the numbers or the values. Okay. However, the problem with this kind of algorithm specification is that it's not precise and unambiguous. Why? Because I mean, if you have just given the instruction like sort in colors, but maybe some guy, some poor guy doesn't know how to sort. Okay, so in that case, you will be confused, like what does it mean by sorting? Okay. However, still, I mean, it's and also sorting by the ranks. If you just specify that sort and omit these statements, then it might be not clear that should you sort in an ascending order or should you sort it in a descending order. But even then, if it's not clear or ambiguous, maybe it's a good start to have some kind of like a sketchy solution. I mean, even if you don't have a complete and precise steps, but it's better than having nothing. So you have at least some initial plan, like what you need to do. And then, as I told you in the beginning, I mean, we don't have any specific kind of a language to write algorithms. It can be written either in your natural language, or it could be written in a programming language, or maybe in a specific format that we call pseudocode. Okay. Each of them have their own kind of advantages and disadvantages. So, for example, of course, the natural language, it's simple to understand. But then the problem with the natural languages is that they are often ambiguous. So, for example, you might have I don't know about the Swedish, but in English, if you have an instructions like don't go, stop, it could be ambiguous. Somebody may interpret it like, okay, don't go, you must stop. But another guy could interpret it in a different way, like go and not stop. So, but then another choice is that the programming language, and the advantage of programming language is that there is no ambiguity. Whatever you have written it must be very clear, and then your algorithm is, you don't need to transform. If you have written an algorithm in a programming language, then you don't need to transform it into a program. It's already a program itself. But then the problem with that is that to use that algorithm, if you have written an algorithm in Java, so then everyone should know the Java to use that algorithm. If a person does not really understand the Java, then that algorithm is not really useful. It's only useful for the guys who knows that specific language, and for the other people it might be not useful. So, and before making, if you have written in maybe Python, so then to use that algorithm, the guy or the audience must have to learn Python first. And then we have a pseudocode, which is like kind of a intermediary middleman approach that combines the concepts from both programming languages and our ordinary natural languages, or maybe the mathematical notations. And as they stand in the middle, so they have the benefits and pros and cons from the both of the other two approaches. So they are, and often we use, when we are using pseudocodes, we don't use the very language specific notations. So instead we use kind of quite simple and generic notations like if, while, and for. These kind of constructs, I think they are quite common in kind of all programming languages. They use similar keywords for iterative statements and selection statements, and they are quite easy to understand. So it's also very important that for the pseudocodes, the constructs that you use, they must be easy to understand. Okay, there is no, there is no standard language to define. To write a pseudocode, you can come up with your own kind of notations. However, what is important is that whatever you write, it must be structured, unambiguous, and easy to understand. Okay, so and then we have the concept of problem solving, which is quite closely related to the algorithms. And an algorithm is basically an approach to solve a problem. So it provides us with the steps to solve a problem. However, a common concept behind problem solving is whenever you have a plan, so even if you don't know anything about algorithms or programming, so let's say we have a common life problem. I want to find a bus from Kalmar to maybe Stockholm. So what steps we need, or maybe if you want to design something like a new chair that suits your requirements, that can be transformed maybe let's say into a table or a bed. So what you need to do is, at first you need to understand the problem, okay? And then once you have understand the problem, what's next? You need to find out some solution. You need to design solutions, okay? And then once you have devised the solution, so the next step is you need to implement, or you need to follow your plan. Otherwise, you will not be able to solve the problem, even if you have a very good design. And after or during the implementation, you must often have a follow-up step. So maybe it could be like the plan or the design that you have come up with to solve the problem. It can work, but it can also doesn't work. So maybe you missed something when you was trying to understand the problem. So if you have understood the problem in a wrong way, you are most likely to end up with the invalid results. It's most likely that it's less likely that if you have a good design and good understanding, then there are quite less chances that you will end up with the wrong results in the end. But if you have understood it in a wrong way, then it's most likely that. So there are some steps from I think this was a Greek guy who took this who presented these 4 steps in the history of problem solving and programming before, although they are quite natural and intuitive steps to solve the problem. And the same problems same approach we often use when we are developing a program or writing a software. Even if you talk about some software, I don't know if you have already studied some software engineering course or not, where we have kind of similar steps, like you need to get the requirements from the user first. It's like and you need to understand the domain first, or the problem first, like a domain analysis. And once you have understood the requirements and the design, and understood the problem, then you need to create some kind of a design, an architecture for your software system. And after you have created the design, like some kind of class diagrams, component diagrams, then you need to maybe implement that design using some implementation programming language of the choice. And after, or maybe you have developed or implemented the program, you need to test it. You need to evaluate it, okay? And another common approach is sometimes it could be that the problem that you are dealing is this much big, and it's quite tricky to solve the whole problem as a whole. In that case, one of the common approach that is used by even the ordinary people who have no computer science or engineering background is like divide and solve or divide and conquer approach. So if you have this much big problem, instead of, for example, if you have like 10 tasks in assignment, so instead of doing all the 10 tasks at a time, maybe you can divide it like, okay, today I will do only just one task. Or maybe even within the task, you can divide it into several subtasks. Okay, so maybe one problem or one assignment task involves more than one or 3-4 different requirements. So instead of doing it all the different things at one time, maybe you break down your problem into smaller chunks, and then you attack or solve those problems one by one. So a simple example over here is like, okay, you invited friends at your home for a party, and there was some food, and at the end, as expected, a lot of dishes. Maybe not in a Swedish home, because most of the people they clean their stuff by themselves, but I don't know if it's the same in the student life or not. And the next morning you need to clean out the dishes. Okay, so one simple way is that you take all the dishes and throw out of the window, but then you lose. But if you decide to clean them, okay, that maybe you have to start somewhere. Okay, you take one plate and clean it, and then you take another one, and of course, if you have a dishwasher, of course, you can put them one by one in the dishwasher. And another thing is that sometimes if you have a problem, and if you need to design a solution for that problem, so maybe instead of thinking the problem in general, it's often we use examples of the problems. So if you work with the examples of problem, and if you can solve a single instance of that problem, maybe then you can also solve other instances of the problem. So it's very useful that if you have a problem, instead of solving the problem itself, take an example or an instance of the problem and try to understand and solve it. And if you have solved it for one instance of the problem, then you can generalize it. Okay, so it's like the other way approach. So instead of solving the general problem, you take a specific instance, solve it, understand it, and solve it. And once you have solved it, a specific instance, then you can come up with a generic solution or general solution to solve similar problems of that kind of nature. And then we have the questions comes in. Of course, when I said that if you have a problem, and there can be a number of different ways, different algorithms to solve that problem. So, but then, for example, if you find out 4 different algorithms to solve a problem, but then you need to find out which one is the best algorithm. So how can you identify which one is the best? What are the factors that you should consider while choosing a best algorithm to solve a problem? Of course, I mean, we already talked about some criteria. Some of the basic criteria to select or find a good algorithm is like, of course, it should be unambiguous, it should be simple and easy to understand, it should provide correct results. But then, other than that, depending on your preferences, what is your definition of good? What is good for you? Is it maybe some guys say that I don't care about resource efficiency. I just need something which is easy to implement and easy to understand. Doesn't matter if it takes 5 seconds or 5 minutes or 5 hours. For that guy, maybe a good algorithm is one that is simple and easy to implement. But then on the other hand, it could be like a company or something which wants to have a faster solutions, or maybe that needs less power resources. So depending on the needs or the preferences, there can be different criteria to choose what is good or what is bad algorithm. And in this course, we will be focusing on time complexity and the time complexity means how much an algorithm is complex in terms of how much time it takes to solve a problem. So it means that in that case, a good algorithm could be a one that takes less time to solve a problem. And to find out, to analyze the different algorithms that performs better, we have one approach with the name of asymptotic analysis. This is also a concept from mathematics. And if you have a function, because an algorithm is more or less similar to a function to solve some problem. Okay, so you have some input, and so in this case, problem that you want to solve is an input, and your algorithm should provide as a result, should work like a function, and it should as an output, it should give you a solution to the problem that you have. And what is important is because when you are talking about asymptotic analysis, the asymptotic analysis considers how your function or how your algorithm behaves when the input becomes complex. So it doesn't really care about simple or smaller instances of a problem, because of course if your problem is small and simple one, your algorithm is likely to solve it in a lesser time. But let's say, for example, if you have to sort maybe an array of only 3 values, a list of 3 values, it's not so big, so maybe any algorithm will just solve it in a matter of seconds. However, if you have a list of, like, let's say 10,000 elements or data values, then it might be different for different algorithms. Okay, so in the asymptotic analysis, we always we don't really bother about smallest or the lowest terms. Instead, we consider only the largest values or the values that are approaching near to the infinity. Okay, so that's why in the asymptotic analysis is an analysis where we analyze the behavior of an algorithm when the input size grows. And it could be like grows in terms of size, or it could grow in terms of complexity. Okay. And here are some general guidelines. So and some notations. So for example, when we are finding an integer in a list, and if you want to find out how much time an algorithm will take to find an integer in a list, on which factor the time depends. Obviously, it will depend on the size of the list. Okay, so if it's a smaller list, it may solve it in a lesser time. But if the size is list is larger, then it could take more time. Similarly, if you have an algorithm to find a prime number, it's again depends on the size of the input. Okay, if it's a smaller value, let's say if it's the value less than 100 or maybe less than 10, if it's a single digit value, you can find like for example, if you want to test 8, whether 8 is a prime or not, you can find 8 maybe only 2 or 3. After 2 or 3 divisions, you will find it whether it's prime or not. But on the other end, if you have to find like whether 800 is a prime number or not, then you have to do it more divisions. Okay, until that you go from starting from the 2 until the number itself. So in that case, again, the time depends on the input size. Okay, so we say that an algorithm have a time complexity O of n if computational time is proportional to n, and n could be n. Here we are considering is the input. Okay, and if the computation time is proportional to n square, then obviously its time complexity will be O of n square. On the other hand, if the time complexity is constant, it doesn't depend on the because for some of the algorithms, it could be that the time complexity is independent of the input size. Whether you use a smaller value or you use a larger value, that algorithm solves the problem in the same amount of time. And if your time complexity remains constant, which is independent of the input size, then we denote it using this big O notation, order of O. Sometimes people call it as a 1. Okay, but in general, we write the complexity as a function O of n if the computation time it takes is proportional to the function n. Okay, and big O or order of O, this is like a notation, a standard notation that we use to measure and estimate and denote time complexity of an algorithm. Okay, and if you have, for example, if you have a method in your program and you want to estimate the time complexity of that method or of that algorithm, we simply consider or assume that the simple instructions, because our program is simply a sequence of instructions. So in your program or in your software, what you have written are the instructions in some special in any programming language. For example, in Java, we have assignment statements, we have iterative loops, selection statements. You might have generics declarations, and you might have exceptions throw and try catch blocks. So we assume that each simple computation, and in this case like addition, because basically what we have are like 4 simple arithmetic operations, and then like plus, minus, subtraction, and divisions and assignments, and all these kind of simple operations. We assume that each one takes a standard unit of time like 1, equal to 1. And then, as I said in the beginning, when we are trying to estimate time complexity of an algorithm, we do not care about smallest factors. We only take the largest factor, because it's like a limiting behavior. Okay, we want to find out for which case that algorithm takes the maximum time, because the statements are the lines which are taking smallest times. They are already covered by the statement that takes most of the times. Okay, so we are interested in a statement that takes most of the time. Okay, so it means that the statement that execute more number of times. Okay, and these kind of statements, they are often part of inner loops, or maybe even a single loops. Okay, because if it's not a part of a loop, if it's a simple statement, then it will most likely will execute only once. But if something you have defined as an iterative statement, so then it's most, or maybe you are calling a method again and again. In that case, like a recursive method, then it will be the call to the recursive method which will take most of the time. Okay, so in this case, for example, here we have a simple lines of code to search a number in an array. So I have a search method, and that search method is taking an array of type integer, and we want to find if that array contains a specific number x or not. Okay, what we usually do when you want to search a value in an array, we start from index 0 and we check until the end, until the last element. And if there is some element that matches to the value that we are looking for, then we return true. Otherwise, we return false, that the value doesn't exist. Okay, so in this case, we know that this statement will execute only once, maybe when the method is called. Okay, this will execute, how much times? Depending on the length of the array. Okay, this for loop, the statements in the for loop will execute n number of times, and here n is size of the array. If the size of the array is 10, this statement, the for loop will execute 10 times. If the size of the array is 100, then it will execute 100 number of times. So in that case, the time complexity of this simple search method is O of n, and n here is the size of the array or size of the input. But on the other hand, if you have another method that is using inner loops or maybe nested loops, it could be number of different scenarios. For example, if you are using a matrix if you are multiplying the matrices, maybe you often use nested loops because you have to do the same operations again and again. You take one row and you multiply with the number of different, one column and multiply by number of different rows, and then you add it, and you have to do it same operation. And even if you are printing a table like this, then also if you see, this statement will execute only once, this will execute n number of times, but this part will execute n multiplied by n, because every time this statement executes, the inner loop will execute n number of times. So n multiplied by n means that n square. So in this case, the time complexity for this print multiplication table will become O of n square. Do you understand? How can we estimate? So it's simply, you have to find out in your program the area or the statements that is going to execute the most number of times. And as I said, it could be iterative statements or it could be recursive calls, most likely. Here are some other equations. So for example, sometimes you might have in your one program, like the example that I give you, it was just different methods. But it could be like in your program, you have more than one methods, okay? And in that case, every method might have a different time complexity, okay? So for example, one of the method you have is 4, complexity 4, n raised to power 4. Another one has n raised to power 3. Okay, so you have to combine them all, like as a plus. But then, to give the overall time complexity of your whole program, once again, you will consider the highest factor over here, because this n raised to power 4, it already covers n raised to power 3, because this is we know that this is going to take lesser time than n raised to power 4. So in that case, we will simply ignore the lower cases, and we can say that the time complexity for this kind of equation is simply summarized or simply simplified as O raised to power O of n raised to power 4. Okay, so we say that if you have a time complexity in terms of like a polynomial equation where you have some coefficients and some variables like n raised to power 3, n raised to power 4, in that case, you can ignore the coefficients or the constant values. So let's say, for example, here you have 3 raised to power n. Okay, in this case, 3 is not something that is very important. What is the important part? Because 3 will always remain 3. It is not going to vary. What is going to vary is the n, and n is usually our input size of the input. Okay, so simple to assume that is that you don't need to worry about the lowest factors or the constant factors, the things that remain constant, that will always remain the same. And also you can ignore the lowest terms, and you can count on the terms or the statements that are going to execute the most number of times. And so here are some common examples of because when you are reading maybe a textbook or some online tutorials, and often when you find out some algorithms, and if you want to look at what is the time complexity of that algorithm is, so often the time complexity is given as a O log of n, O of n raised to power 2 or 3. So in order to understand which one is the fastest or which one is the slowest, of course, if it's the fastest one, will be the one that has a constant. Okay, so O of 1, that is the most fastest one, that takes less amount of time. And then if it's like a logarithmic kind of a function, so then O log of n is the next. And then you have if you have algorithm that takes that's time complexity is dependent or proportional to the input size O of n, and then it comes to the exponential, like n raised to power 2, 3, 4, n. So that will take most number of time. Okay, I think before going to this part, maybe we should take 10 minutes break. And before going to the break, if you have questions regarding the part that we covered so far, of course, you are welcome. Otherwise, let's meet after 10 minutes. Okay. Yes, we have talked about the time complexity and how can what are the factors that you need to consider when you are estimating the time complexity for your algorithm. And in this second half, we will be looking at few of the commonly used algorithm for searching and sorting, and why these two operations, because it's one of the most commonly used operations. Because often in your programming, either you are searching for some values or maybe you are sorting the data, and then we will see for the commonly used algorithms, we will also see what are their time complexity estimates. Okay, so starting with the sorting first. So one of the commonly used simple algorithm, if you have an array of integers and if you want to sort it, a common approach is that you are often either knowingly or not knowingly you are using a selection sort. You are selecting a smallest value, and you start from the first index and you go until the last, and you pick in a several iterations, you pick smallest value and you bring it to the first position if you are sorting it in a ascending order. Okay, so the simple steps are like, if you have a list of n elements, you find the smallest of the numbers and swap with the first element, and after that, because you have, it means that your first element is now in the right position, then you start from the second element and you go until the last element, and then pick the smallest values among the remaining elements, and you place it on the second position, and then from until the nth position you keep on iterating this. So for example, here if you have a list like this, which is like an array and it's unsorted, so we start from here, and in the first iteration we find the smallest value. So which one is the smallest value here? I think it's -12. So you find the -12 and you swap it. Swapping means like you replace. So you take 12, -12, and you take to the first position, and you move 6 to the position of 12th element, -12. Okay, and in the next, so now you have a -12 which is at the right position. So now you consider this part from second element until last, and it's the -7 is the smallest value. So in this case, you will not need to, I mean, even if you do the swap, it will make no effect in your array. Okay, and continuously you go in every step until the last step where you get the smallest value. And then I mean, here you also have an algorithm for this selection sort. And if I ask you, because if you see that here we have a list from with the index, of course, in a programming we have index 0, but if you are using a pseudocode, and pseudocode doesn't need to be programming language specific, so it could be like your own notations. And from, let's say we have an index starting from value 1, and then we have an L element. So, and what we need to find is, in each iteration we need to find the smallest index, smallest value, and we assume that initially in the first iteration our first element has a smallest value, and then we check, compare it with all the other elements, and if the other element, if you find a new smallest value, you replace it. Okay, so, and in this case, if I ask you to estimate the time complexity for this algorithm, could you give me some estimate? Could you see, analyze which part of this pseudocode or the algorithm is going to execute the most number of times, and how many number of times exactly? Yes.
Will the for each loop execute n number of times?
Sorry.
Will the for each loop execute n number of times?
Which one? Yeah. Yes. This will execute n number of times.
Okay.
Because it says like for each I belongs to 1 to n minus of 1, so it's almost like n number of times. but then you also have in this for each loop you have another for each loop that also executes more or less on n number of times. So which part will execute the most number of times? Yeah. Every time this outer loop executes, this inner loops execute more or less, because if you consider the first case where the value starts from 1, starting from the first index to n, this will also execute n square number of times. Okay, so in this case the time complexity will be for this is like proportional to your depending on the size. Okay, n is the size of your array, so we can say that the time complexity is because the inner loop is executed roughly n square times. So from here we can get that this if you implement selection sort and then the selection sort will take n square times, and here n square is the size of your array to sort your list or data. This is just Java implementation of the algorithm that you have seen before. And then we have another algorithm, insertion sort, and in this algorithm what we do is that it's the same, that you have a list of some values, or it could be like integer values, and then if you want to sort them, instead of we assume that we have the first element that we have in the array, it's already sorted one. So we start from the second element and we place it in the right position among the first two. Okay, so it means that if you have an array like this, 6 minus 7, 9, 12, so you take this minus 7 and you compare it with the first element, and you see if it's smaller than, then you replace it with this one. Otherwise it will remain at its own position. And once you are done with the second, then you take the third element and you compare it with the first three and do it in a right position. Okay, so and then you continue every time. But if you see here, can you give me any idea that if you have to implement this algorithm, what will be the time complexity of this one? How many, which part will take, will execute most number of times? Because n is again the size of your array. It will be more or less the same, because if you consider, I mean, like the last case, for example here, for the nth element, we have to compare it with all the other nth elements. And you are doing it for all, I mean, if you see, when you are starting from the second element, and then you continue from second to 3, 4, 5, you are doing it n number of times. And for each iteration, you are again comparing it with the elements on the left. Okay, so in this case we can say that the time complexity of insertion sort is n square. That is more or less same that than we have for the selection sort. However, for some scenarios, insertion sort performs better than selection sort. And what is that scenario is, if you have already a sorted list, then you, because if you use the selection sort, it will always do the same operation. Doesn't matter if you have a list which is already sorted one. But on the other hand, if you have a sorted, if you are using insertion sort algorithm, only your outer loop will execute, your inner loop will not execute, because the condition becomes false over there. So in that case, so it means that because when you are using an algorithm and you are getting a values, so you don't really know what kind of values you will get as an input. It could be. So it means that this insertion sort has a slight advantage over selection sort. So it could be, it can perform better on a sorted list. Okay, but still, I mean, as a worst case time estimate, it still has a time complexity of O, big O of n square. So we have seen two sorting algorithms, and we will see another sorting algorithm more towards the end of this lecture, which is that uses divide and merge sort algorithm, where you divide recursively, and we will see that it has a better time complexity estimate that takes much less time as compared to selection sort or insertion sort. But before that, we have searching algorithms. We have this linear search algorithm, where you start from a first index and you linearly go from first element until to the end of the element to find whether this value exists or not. So in this case, so for example, if you have this linear search method over here that takes two arguments, or the first one is an integer array and the second one is the element that you want to find. Okay, so in this case, as I said, that you have to start from the first element and then you have to compare until, because you don't know it. It could be, I mean, in a simple case, it can be that you find the value at the first index, then your loop will execute only once. But it could also be that that element does not even exist. In that case, you have to go through all the elements. Okay, so and to give us this time complexity estimate, there can be different categories. Like often we have like a best case, like how much in a simple example like this, as I said, that the best case will be when you find the element at the first position, and it could also be like the average case and the time complexity estimate, like on average how much time this algorithm takes. But then it could also be like a worst case, and we are more concerned with the worst case analysis over here for the asymptotic analysis, like how much time maximum an algorithm can take. Okay, so for example, if the element does not exist, or if the element exists on a last position, then it's like a kind of a worst case, and where you have to perform this algorithm as a full. So in this case, the time complexity for this linear search algorithm will be proportional to size of array n. Okay, so we can say that big O of n. Yeah, and then the question is, I mean, do we have like a better algorithms than this? Of course, yes. You have already seen binary search trees. Okay, and what do we do in the binary search tree? If you have to search in a binary search tree, you start from the root, and then you compare the value that you want to search with the root, and if the value is lower than the root element, then you go to the left subtree, because you know that in the binary search tree, the left subtree or the left children are smaller than the root or the parent itself, and on the right subtree you have all the larger values. Okay, so basically what you're doing is that you are on every step you are dividing your problem into half. Okay, so and on the same basis we have the binary search algorithm, and in the binary search algorithm, if you have a list of elements, what you do is, for example, here you have a list 1, 3, 5, 7, and also a very important step for this algorithm is that the list that you want to search, on which you want to apply this binary search algorithm, it must be a sorted list. Otherwise, this algorithm is not going to work. And we know that the binary search tree is already like the values are sorted in an order. Okay, and so starting you take for this algorithm you take the array, the value, and then you compute the middle value. You find the middle value and you compare the middle value with the value that you are looking for. And there could be like three cases. Either the value is the same, is equal to the middle value. In that case, you have already found the value. You don't need to go further. But if that value is not equal to the value that you are looking for, then it could be either less than or greater than. And if it's the less than, then you have to look at in the left part from 0 until middle position minus 1. But on the other hand, if it's more toward the, if it's a greater, then you have to go to the right part. Okay. So for example, here find 8, okay, and the middle position in this case it's like 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So like you can either choose 7 or 8 as the middle value, up to you. Okay. And in this case, let's say if the 7 is the middle value, so and 8 is greater than 7, it means that we can ignore this part and we have to focus on this part. Okay. And then on this part again, 8, 9, 10. Okay, in this case, yeah, from 8, 9, 10, and we say middle value, the middle value over here is 9, and 8 is less than 9. It means that we have to look at into left part, and in the left part we only have 8. And when we try to compute, because 1 you cannot divide it further, so that's your last case. And if you find the value, it means that you have find it. Otherwise, if there is, that value does not exist in your array. Okay. So if I ask you to estimate, if somebody asks you to estimate the time complexity for this binary search algorithm, then can you give me some estimate, like is there some relationship between the time and the input size? It's more or less if the input size is 1, as it in a simple case over here, how many steps you will need? You will need only 1 step. Okay. And what if the input size is 2? How many steps you need? 2. Okay. And like this, if the input size is like 8, 1, 2, 3, 4, more or less 3, 2 raised to power 3. Okay. If the size is like 1, you can find your solution just in a 1 step. 2 to maybe 4. So it means that from here we can generalize that the time that you need and the size, they have this 2 raised to power p. Okay. Or maybe you can say 2 raised to power n if you are talking about more in terms of n. And we can say that the input, or maybe the size, as a function of time, and then if you inverse this function, you will get this log of 2 into 1, because we know that if you from the mathematics we know that its logarithm is an inverse of exponents. Okay. So in that case, we can say that the time complexity for our binary search algorithm is log 2 of n. And why log 2 of n? Because we, at every step, we divide our problem into halves. Okay. So in this case, we can say that as compared to the linear search, because in the linear search, the time complexity was O of n. It means that it takes n number of times, and n is the input size. And as compared to that, the binary search has a better time complexity. It means that it's more efficient. It will take less number of steps, less amount of time to search a value in a data structure. And this is just Java implementation, that how can you recursively implement this algorithm. So for example, in this case, we have a method, recursive binary search, and it takes an array in which we want to search and then value that we want to search. Okay, and we need two variables to find the middle, like the minimum position and the maximum position, and from that position we can find out what is the middle value. And then we have another method with the name of binary search, which is actually a recursive one, and we pass that array in which we want to look, and the value, and the starting position, and the ending position. And the first time we look, if you find the value, middle value, which is exactly the same as the n that you are looking for, you can return true, and then in that case you don't need to go any further. But if the value is not found, in that case, if n is less than the middle value, it means then you have to go to the starting, the first half. So you call this method again in the return statement. What you are doing, you are calling the method same method again as a recursive call. Okay, array, integer, min, but the max is now mid minus 1, because I don't want to look into the part that is on the right side of the middle. But if it's on the middle, if it's the value that you are looking for is greater than the middle value, it means then I need to look for on the right side. So in that case, our min will now become mid plus 1. So starting index will be middle plus 1 until the max value, limit value. You understand how does it solves? And the next thing is, we have also seen hash table. And in the hash tables, we know that we use hash functions, and we take our data, and on that data we apply a hash function, and we use the value returned by a hash function as an index. Okay, so if you have to find a value in a hash table, doesn't matter the size, how many, even if you have like 10,000 values in your hash table, it always, and if you want to, you use a value that you want to look at, and you call the hash function, and on that index it directly points you to that index. So it means that in case of a hash table, the time to search is independent of the size, the input list. So then it means if we use the hash table as a data structure, the time complexity will be a constant. Okay, so O of 1, a fixed number of computations independent of the size. So it means that, and we know that if time complexity is not dependent on any input size, then it's a constant factor. Okay, and on the other hand, for the binary search tree, if you have used the binary search tree, that works similar to the binary search algorithm. We will again, for the binary search tree data structure, the time complexity will be again log 2 of n. The last, we have a merge sort algorithm, and we already have seen two algorithms to sort the data, selection sort and insertion sort, and we saw that both have time complexity of n square. But then we have this a bit efficient algorithm, and it actually uses divide and conquer approach. Okay, recursively it takes an array of size n, and then it divides it until you get single element in each part. Okay, so let's say if you have this array of size 7, so you divide it into 2 halves. Okay, so one half will get 4, another one will get 3. Then you take this one and divide it into another halves, and you keep it dividing into halves until you get just one element in each part. And on that part, so here we have dividing the array. But then once you have been gone to the lowest possible size, you start merging them. And while you are merging them, at the same time, you put the elements in the right position. So for example, when we merge 38 and 27, we will put them at a right place. So 27 will go here and 38 will go next. Similarly, we take these two parts and we merge them. So 3 comes here, 43 comes, go on, depending on the order in which order you want to sort your data. If you are sorting it in ascending order, then the smallest value should come first. And after that, on the next step, you combine these two values. And when you combine these two values, you again sort the values over here. Okay, so we have 2 basic kinds of operation. The first operation was we divide. Okay, and if you see, the divide is kind of similar to the binary search, and in the binary search we also divide and then see. So for the division part, the complexity we have is log 2 of n. But then when we are merging them, we also, depending on the number of elements, here we have n is 1, here n is 2, here n becomes 4, here n becomes 7. So at each level, we also have this task of sorting them when we are merging them. So it means that the overall time complexity of this merge sort approach will be O of n dot multiplied by log 2 of n, because we have 2 different parts here. We have one part which is dividing, and we have another part in which we take the smallest or the level that we have divided, and on each level, depending on the size n, a level could be of size 1, it could be of size 2, 3, 4, up to don't know how many levels you have, depending on your initial input array. But if you compare this one with n square, this is still better, because it is n not multiplied by n, but multiplied by log of n. So it means this merge sort, if you have a, it might be not very important if you have a only smaller set of data, like maybe 300, 400, you can use any algorithm and you will not notice the performance. But imagine if you have a huge, like a national database, where you have data for all the population in a country, and it means that you are dealing with maybe 10,000 or 100,000 of records. And in that case, if you want to give our customers not too time-consuming behavior, then you have to think about more better or time-efficient algorithms while you are implementing your algorithm. Okay, and this is just an outline of the algorithm that we start from the level, starting from the first level, and then we go until the size is 1, and the size 1 means that array is, of course, if it's only one value, we assume that it's already sorted, and then we start calling. And if you are implementing it, you can also implement it and in a recursive way. Okay, So you can have like as we have like middle and left part and the right part. In the same way, you can also have a left sort and right sort. Okay, and in the end, you can combine them. However, a problem with this kind of algorithm is that it might be if you do not reuse the array that you pass, because if you every time you create a new array, then it might be more time, memory. It will take more memory. Okay, space will be more. So, but I mean, of course, you can reuse the same array. If you work on the index values instead of creating a new array, you just take the index values as you done with the binary search algorithm. And in that case, you don't need to, I mean, you can preserve the memory. So even being time efficient, you don't need to create, I mean, at each step, you don't need to create a new array. You can reuse the same array, but it can be tricky to keep track of indexes. Okay. So I think this brings us to the end of today's lecture. And next we will have, I think, the last lecture that will be more about the formal languages, regular expressions, and the context-free grammars, parsing. And before that, if you have any questions, of course, you can ask now or maybe even later whenever you have. Okay? So thank you so much. What do you mean by using?
I mean, are we going to have to implement it in the assignment at some point, in the fourth assignment?
Most likely not, but no promise yet.
Oh man, come on.
Most likely not.